Good morning. The topic that we are going to discuss today is the electric flux, and related to it is the important one that is called as Gauss's law or the Gauss's theorem. Now, before starting with this electric flux, the Gauss theorem, let us have a quick revision of what we studied in the class, in the last few classes. So we discussed about what is called as electric field or the electric field intensity. Okay, so we know that the electric field intensity at a point due to a point charge, suppose that point charge is Q, and from this point charge Q at a distance r, if I assume a small test charge is placed, then by Coulomb's law, this source charge will exert a force on this test charge, and the magnitude of that force will be given by Coulomb's law. And according to Coulomb's law, the force that this charge is exerting on this test charge will be repulsive in nature, because both the charges, they are positive. So if I assume this F is that repulsive force that this source charge is exerting on this test charge, and the magnitude is given by F is equal to some constant 1 by 4 pi epsilon 0, we have discussed this in the class, multiplied by Q into Q naught divided by R square, and the direction of this force will be from Q to Q naught, as is the repulsive force. As far as the electric field intensity E at this very point is concerned, that is given by E is equal to F divided by Q0. So the electrostatic force per unit test charge gives us the electric field intensity at a given point because of this source charge. And mathematically, if I see this E is equal to F upon Q0, therefore what I left with is 1 upon 4 pi epsilon 0 Q divided by R square. So in this very expression of electric field intensity is 1 by 4 pi epsilon 0 is a constant, the magnitude of the source charge is constant, what is variable is this distance R. Now as soon as this R is increasing, the intensity of the electric field at those points will start decreasing. So your electric field is varying like 1 by R square, that is electric field is inversely proportional to the square of the distance between the source charge and the test charge. Up to this point we have discussed in the class. Also we discussed about the electric field lines. So electric field lines are the imaginary lines along which a test charge will move under the attractive or the repulsive force of a source charge. So those imaginary lines are called as the electric field lines or electric lines of forces. Let us now come to our today's main topic, that is electric flux, and the topic related to that would be the Gauss's theorem. Let us now start with the concept of electric flux. So what electric flux basically is. In order to understand the concept of electric flux, the symbol for this electric flux is phi and this E. So phi is the symbol for flux and E for the electric flux. Okay, the electric field. So this phi E is representing the electric flux. Now, in order to understand the concept of electric flux, I have to define two important terms. Number one, we will define what is called as the area vector, and number two, we will define the solid angle. What a vector quantity is, we know very well. What an angle is, we know very well. But you have to see these two things from a different perspective. is area. Now area in general is a scalar quantity. It has only magnitude but there is no direction. For example, if I take a circle, then a circle of radius r will be having the area pi r square. But here, for considering the electric flux, we have to treat our area as a vector quantity. So along with magnitude, it will be having direction also. Now what will be giving us a direction? Let us see. So how do we define an area vector? Okay. For example, if I consider a circle, suppose a circle whose plane is perpendicular to this board, and suppose if this O is the center of this circle and R is its radius, then of course the magnitude of this area of this circle would be pi multiplied by r square. But a vector quantity needs a direction also. So how to assign the direction to this area? For that, what we will do, to the plane of this circle, we will draw an outward perpendicular. We also call it as outward normal. So that outward normal drawn to this circle, for example here, if I represent it by n cap. Now what this n cap is, this n cap is the unit vector which is normal to the plane of this circle. So this n cap is the unit vector. So if I want to write this area in terms of vector, we know that we write a vector quantity, suppose this area A vector as the magnitude and the direction. So what I have written here is A vector is equal to A into n cap. What this A is the magnitude of the area of this circle, that is pi r square, and this n cap is representing the direction of that area, that is the direction of my area vector. Now this n cap is the unit vector always drawn normally outward. Is always drawn outward normally. Okay. Now, in order to understand this, for example, if I take this as my area, this suppose the area, the cross section of this area would be a rectangle. Now the area vector would be in this direction. This is the outward norm that is coming out of this area. If I tilt it like this, my area vector will go like this. If I tilt it like this, my area vector will be coming towards u. If I keep it down, the area vector will be in the downward direction. So what to keep in mind while defining the area vector is the direction of the area vector is always drawn outward normal to the surface. That should be uniquely defined. Next comes the solid angle. Up to this point, we know what an angle is. For example, if I take a circular arc, this is a circular arc, and suppose this is the center of that circular arc O, and if I consider this R as the radius of the circular arc, and this, if I give this AB name to this circular arc, then the angle that this circular arc is subtending at the center, we write it as theta. So this theta would be given by the measure of the length of this circular arc AB divided by the radius of the circle of which this arc is a part. So the angle in general we define as the arc divided by the radius, the length of the arc divided by radius. And of course angle is a dimensionless quantity, nevertheless it has unit. So we define this angle as the arc upon radius, and the unit of that is radian. But this angle which is arc is subtending at this point is known as a plane angle. And a plane angle is always a two-dimensional angle. Is a two-dimensional angle. Now, what we are interested in is the solid angle. It is related to this, but unlike plane angle, this solid angle is a kind of three-dimensional angle. A three-dimensional angle. Suppose if I consider myself inside a balloon or inside a sphere, then if I consider the part of the surface area of that sphere, and suppose if I am standing or sitting at the center of the sphere, then that part of the surface will be subtending an angle at the center. So suppose if I consider this as that surface, so if I am sitting over here, then all these points of the surface, they will be subtending certain amount of angle at this very point. Now this angle, unlike this angle, it will be three-dimensional angle because it is subtended by the whole surface at a particular point. This plane angle was subtended by a linear arc at a particular point. Therefore, we call this angle as two-dimensional angle and we call this angle as the three-dimensional angle. So, like the unit of the plane angle is radian, the unit of the solid angle is steradian. Steradian, we write it as SR. Like a complete circle subtends an angle of 2 pi radian at the center of the circle. Therefore, if I consider myself inside a sphere of radius r, then the whole sphere will be subtending an angle of 4 pi steradian at the center of the sphere. So, this is 4 pi steradian is the solid angle. The 2 pi radian is the plane angle. So we will be needing the use of this solid angle when we discuss about what is called as the Gauss's law or the Gauss's theorem, right? So these were the two important definitions. One is the area vector, second is the solid angle. Let us now come to the concept of what is called as electric flux. So this electric flux is basically a measure of the number of electric field lines which are passing through a surface. Electric flux, we denoted it by phi E, is a measure of the number of electric field lines passing through a given surface. More the number of lines passing through a surface, we call it as more the electric flux passing through that. Okay, and later on you will see that more the number of electric flux passing through that will be related to the electric field intensity at a given point from that surface, and that will be the topic of what is called as Gauss's theorem. So for having a clear understanding of Gauss's theorem, what we require to have is a transparency in the concept of electric flux. The electric flux is very important. It may seem to be very easy for you, but it is not that easy. So what electric flux is? So electric flux we define, for example, if I consider a charge, let us say Q here. Of course, this charge will be my source charge. And this charge is at a distance of suppose r from a given test charge. So consider that test charge as plus Q0. Okay, then if I enclose this charge in an hypothetical surface, hypothetical means the imaginary surface, that surface, it may be a sphere. A sphere, suppose if I construct a sphere, something like this. So the surface area of this sphere, this is my sphere. The surface area of that sphere would be A is equal to 4 pi r square, because r is the radius. So any point if I take on this sphere will be at the same distance from this source charge, and therefore this r will become the radius of the sphere, and this a is equal to 4 pi r square will become what? The surface area. Okay, now let us see the concept of the electric flux. What electric flux basically is, suppose at this very point, if I consider a very small area of this sphere, it is a sphere, mind, it is not a circle. It may look like a circle, but it is basically a three-dimensional sphere, something like this. Your source charge is enclosed right in that particular sphere. Okay, so this is a closed surface. This is an example of what is called as a closed surface, because your charge is enclosed inside that surface, right? So therefore, if I consider at this very point a very small area of this whole sphere, something like this. So since this surface, if I call it as dA, so this d, what is dA basically is, dA is the magnitude of the area of this very small surface which I have taken out from this whole sphere, and therefore we call this dA as the area element. We call it as what? The area element, because it is a very small part of this whole sphere having area A is equal to 4 pi r square. So I know the area of the whole sphere, that is 4 pi r square. I don't know what is the area of this area element, because it's a very small part of this whole sphere. Now again, what electric flux is? If I take the area vector, so we define area vector as magnitude of the area vector would be dA, and its direction is given by the outward normal drawn to the area. Now since we have taken this surface as the sphere, and therefore the direction of the area vector, that is outward normal drawn to that, would always be radially outward. Here will always be radially outward. Okay, we define this phi E, that is the electric flux, as the dot product of E and dA. E dot dA. What E here is? E is the electric field intensity. The electric field intensity at this very point where we have placed our test charge. Okay. Now here, if you look at the direction of this electric field, it will also be radially outward. Here, also radially outward, something like this, because this is the source charge which is positive, this is the test charge which is also positive. So the electric field would be repulsive, and it will be along this radius, and therefore we can say that the angle theta between E and dA would be equal to 0 degree. Would be equal to 0 degree. So this phi E is equal to E dot dA, and that would be equal to what? E into dA into cos theta. So phi E is equal to E into dA into cos theta. Now since theta is equal to 0 degree, what we can write here is E into A into cos 0 degree, and we know that the value of cos 0 degree is 1. Therefore, for this particular case, the flux phi E is equal to E into dA. You should write dA over here. E into dA into 1, because cos 0 is equal to 1. So what this phi E basically is? Phi E is the number of field lines that is passing through this very small area element of this whole sphere. Okay, what this phi E is? The number of field lines, is the measure of the number of field lines passing through this very small area element dA. If I want to find the electric flux through this whole sphere, I know a small quantity, I have to calculate a larger quantity which is based on that smaller quantity. What I will do is very simple, I have to do the integration. Okay, so the integration, so the flux through the whole sphere, a flux to the whole sphere, if I consider it as capital phi E, would be given by integration of this small phi E. What small phi E is? Small phi E is the flux through this very small surface. Okay, so if I put the value of phi E over here, if I put the value of this phi E over here, and as phi E would be equal to E multiplied by dA. Now since this electric field intensity would be constant in magnitude over the whole surface of this sphere, therefore I can take this E out of the integral sign. So the flux through this whole sphere phi E would be equal to E into integral dA. And now since we are performing this integration over the whole surface, so what the whole integration would be giving me is E into 4 pi r square. So the flux which is coming out from that sphere would be 4 pi r square. This is the concept of the electric flux. So what electric flux basically is? Electric flux is the measure of the number of field lines that are passing through a given surface. Okay, this is what the electric flux is. And the electric flux, the magnitude of the electric flux, it depends on three things. If you look at the formula, the mathematical formula for the flux. Number one, it depends on the value of the electric field intensity at that point. It depends on the magnitude of the area. Okay, along with these two, it also depends on the angle between the electric field vector and the area vector. Like in this case, theta was equal to 0 degree and therefore the flux was maximum. If I take any different surface, then the angle between this n cap and this n cap and E vector would be different, and therefore this flux would be different. Okay. Suppose again, if I consider a given surface, something like this, if I consider it like this, if I keep my electric field in this direction, suppose my electric field lines are coming in this direction, okay, area vector is also in the same direction, that's like this case. So this theta would be equal to what? Theta would be equal to 0 degree. And therefore, the maximum flux is passing through this. Now suppose if I keep my electric field in this direction only, electric field is from downward to the upward direction. And now suppose if I keep on rotating my surface like this, what is changing here is not the electric field but the area vector. Okay. Now keeping the electric field constant in this direction, if I keep on rotating the surface, at one particular stage, when my surface becomes something like this, okay, now what is happening? Electric field is in this direction, my area vector is in this direction, because the area vector is always outward drawn normal. So now the angle is 90 degree. My area vector is in this direction and the electric field is in this direction. So the angle is 90 degree now. So when I look at this formula, this phi E would be equal to E into dA into cos 90 degree. And the value of cos 90 degree is 0. And therefore, no flux is coming out from this surface in this particular case. So, and therefore we define electric flux as the measure of the number of field lines passing through that surface. Now when we have this case, when the area vector is perpendicular to the electric field, there is no field lines coming out from this surface, and therefore we say that the value of the flux is 0. Okay, this is what the physical meaning of the electric flux is. So I am repeating, Electric flux is the measure of the number of field lines passing through an area, and that area should be kept normal to the electric field. Okay, if you look at this is E into dA into cos theta is the mathematical formula for calculating the electric flux through a given surface. Okay, so when theta is equal to 0 degree, the flux passing through a given surface is maximum, and when theta is 90 degree, that is when the area vector and the electric field vector, they are perpendicular to each other, there is no electric flux passing through that. So the flux would be equal to 0. Now, having a little understanding of this electric flux, let us now come to what is called as this Gauss's theorem, or it is also called as Gauss's law. This Gauss's law is related to the electric flux that we have defined. The statement is, before stating this Gauss's theorem or the Gauss's law, you have to keep in mind, you have to choose a surface. That surface should be a closed one. The examples of closed surfaces, you may take a balloon, you may take a sphere like a ball, you may also take a potato bag. Why do we require to take a closed surfaces? Because your charge for which you have to find electric flux should be enclosed inside that closed surface. Okay, and we call that closed surface, from now onwards, we'll call that closed surface as the Gaussian surface. So we call that closed surface as the Gaussian surface. So for dealing any problem for this Gauss's theorem or the Gauss's law, we have to choose a surface, a closed surface, and we call that closed surface as the Gaussian surface. Okay, it is applicable only for the closed surface. I cannot take a handkerchief or a piece of paper because that will be an open surface. You cannot enclose anything inside paper. It is very thin. It is very thin means it is two-dimensional. So it is a plane. So it is not a closed surface. It is an open surface. Okay. Gauss theorem is not applicable for the open surfaces. You have to use a closed surface which is called as Gaussian surface. Let us state this Gauss's theorem. It says that the statement of this Gauss's theorem or the Gauss's law, it states that the net electric flux through a closed surface is equal to 1 upon epsilon 0 times the net charge present inside that closed surface. Inside that closed surface. The statement is very simple. The net electric flux, why I am calling it as net, we will see later. The net electric flux through a closed surface is equal to 1 upon epsilon 0 times the net charge present inside that closed surface. Okay. So, if I write it in the mathematical form, if I write this phi E is the net electric flux coming out from that closed surface. We have defined it as like E dot dA, and that would be equal to 1 upon epsilon 0 times the net charge present inside that closed surface. This is the mathematical form of what is called as the Gauss's theorem. If we take again a simple example of a source charge which is enclosed inside a closed surface. For example, again the sphere. Spherical symmetry is the most common as far as electrostatics is concerned. So we will take the example of the sphere again. If I take a sphere, something like this, and at the center of this sphere, let us say O, I keep a source charge, let us say plus Q, and on the surface of it, if I take a unit positive charge, then here if I consider R as the radius of that sphere, R is the radius of that sphere, then the electric field intensity at this point P, this P is my observation point. The electric field at this point P, from Coulomb's I can very well write E is equal to 1 upon 4 pi epsilon 0 is Q divided by R square, because here I have kept a unit positive charge, and therefore the electric field intensity at this point because of this source charge would be given by 1 by 4 pi epsilon 0 Q upon R square, right? And therefore if I consider again my net flux through this whole sphere, so that would be very easy for me. So this phi E would be equal to, I know that it will be giving me E multiplied by A, where this phi is the flux coming out from this whole sphere, that is equal to E into A, because at every point the electric field and the area vector, they will be in the same direction, right? Because it is radially outward, both. The electric field would be radially outward as well as the area vector would also be radially outward, because at every point the area vector would be along the outward drawn normal, that is along the radius, right? So the total flux phi E coming out of this sphere, phi E is equal to E into A. Now when I keep the value of E and A here, what I left with is, since E is equal to 1 upon 4 pi epsilon 0 into Q divided by R square, this is the electric field, and if I multiply it by the area, because phi E is equal to E into A, what is the area of this whole sphere is 4 pi R square. So this 4 pi would get cancelled by this 4 pi, and what I left, this R square would get cancelled by this R square, and therefore the flux, the net flux that is coming out of this spherical surface would be Q divided by epsilon 0. This is nothing but the restatement of my Gauss's theorem. Okay, so the Gauss theorem says that the net electric flux through any closed surface is 1 upon epsilon 0 times the net charge present inside. The statement is very simple, both the verbal statement as well as the mathematical statement. What is important thing that should be kept in mind is the flux. The flux through this whole surface is independent of the radius of this sphere. Whether I take my sphere this small or how big, my flux is remaining constant, is independent of this R, that is the radius. What would be changing here, of course, is the electric field intensity. Okay, but the electric field intensity multiplied by the area would always be a constant phi E, right? So this electric flux, the net electric flux through any closed surface is 1 upon epsilon 0 times the net charge present inside it. I have written the word net flux and net charge. Why? Because if I take a negative source charge over here, then my electric field would be in this direction. My electric field lines would be entering into the sphere. Okay, but the area vector would be along this. So when I take a negative source charge, the area vector and the electric field, that they would be forming an angle of 180 degree with respect to each other. Okay, and therefore that would be E dA cos 180 degrees minus 1, and therefore there would be a net flux coming into the surface. For this positive charge, the flux is going out of the sphere. For the negative charge, the flux would be coming into the sphere, right? So this thing should be kept in mind. The net charge, okay, it is also very important. Suppose I have taken a positive charge over here, so the net charge is positive because only one charge is present over here. But suppose if I take many charges inside this sphere, for example, at this very point only, if I take, suppose if I put many charges, some positive, some negative, then the net charge over here would be the algebraic sum of all those charges. Now positive plus negative plus positive plus negative, what is the resultant that you do take into account while calculating the flux? If the net charge is positive, the flux would be moving away from the sphere, that is outside the sphere. If the net charge is negative, the flux would be coming into the sphere. Okay, so this thing you should keep in mind. If I give a very small problem, we consider an electric dipole. We have discussed in the class that an electric dipole is a system of two equal and opposite charges kept at certain distance. So we call it as electric dipole. If I take a cube, for example this room only, so if I take a cube and if I put an electric dipole inside this room, okay, the net electric flux coming out from this cube or coming into this cube from this Gauss theorem, if someone asks to calculate, the answer should be very simple. And obviously it should be 0. Why 0? Because for an electric dipole, if you look at the net charge, the total positive charge is equal to total negative charge, and therefore the plus minus is 0. Okay, so for example here 2 microcoulomb, here minus 2 microcoulomb, and that is an electric dipole. Okay, then the total charge would be equal to 0, and therefore the flux coming out of that cube would be equal to 0. What is the meaning of net flux 0? The number of field lines moving outside the cube will be exactly equal to the number of field lines coming into the cube, and therefore they will be cancelling out each other, and the net flux would be equal to 0. So this is about your Gauss theorem. In the next class, we will be looking at the application for this Gauss theorem. This Gauss theorem is basically used for calculating the electric field at a point because of different charge distributions. For our board class, we have 3 types of distributions in our course. Number 1 is the linear charge distribution, that is the charge will be spreading along an infinite line. That is called the linear charge distribution. Secondly, the charge will be distributed on an infinite plane sheet of charge. Okay, I will be giving you a surface, a plane surface, and going to find the electric field at a point because of the infinite plane sheet of charge. This is the second application we will be seeing. 3, last but not the least, we will be having a sphere, and a certain amount of charge will be spreading on the whole sphere, and we have to find the electric field because of this charge distribution, this spherical charge distribution, inside the sphere, on the surface of the sphere, and outside the sphere. So in the next class, we will be discussing the applications of this Gauss theorem. Wait up to it. Thank you so much.